Okay, we're doing complex roots of a quadratic equation. So we're going back to looking at parabolas, and we're going back to either completing the square or the quadratic formula, because that is how we find the root of any quadratic equation. So first, we understand that we are looking only at quadratics. We're not trying to find the roots of cubics or quarts, simply quadratics. So that means our friend the parabola over here. So remember, a quadratic can do three things. It can cross the x-axis once, as if this were the equation x plus 3 squared. Remember, its root would be where x is a negative 3. So there it is, crossing at negative 3. It can cross the equation twice. It can cross the x-axis twice. And here the roots would be 1 and 7. So it would look something like that, as close as I can get it. And it can cross never, and that's what we're going to look at today. So if I were to show you x squared plus 9, it would be the parabola all the way up there, and that's what gets complex about it, because in this case is when you will have imaginary roots. So if we were to solve x squared plus 9 equals 0, x squared equals negative 9. When we take the square root of negative 9, remember, always put plus or minus, we see that it's imaginary. So the answers here are plus or minus 3i. So that's all we're going to be doing today. We're going to be doing either the quadratic formula to find the roots or completing the square. And to tell you the truth, I bounce between the two depending on how easy the leading coefficient and the b value look. So for example, if you were to give me this number 1, I would immediately go for completing the square. There is no leading coefficient, and taking half of negative 6 seems real easy. So if I go to solve this, x squared minus 6x plus 13, we set it equal to 0. That's what the x-axis represents, where the y values are 0. I'm going to go forward with completing the square, which means I get the x's alone by moving the constant over to the right side. I now take half the b value, and hopefully by completing the square, you can do a lot of short steps right now. I know that this is going to be x minus 3, quantity squared, because half of negative 6 is negative 3. Now, in my mind, again, this is a shortcut. Let me straighten that out again. This is a shortcut. This is how I see it. I see that that negative 3 squared is positive 9. So in my mind, I know I had to have added 9 onto this side. That's how it was x minus 3 quantity squared. Negative 3 plus 9 is negative 4. So I'm left with x minus 3 quantity squared equals negative 4. And now I want to find my roots. I know I take the square root of negative 4, and then this 3 comes over as positive 3. So x equals 3 plus or minus 2i. Now really you should be able to do the completing the square quite quickly. But if you still want to grind out the quadratic, here it is. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Just please make sure you take the time to really know what your values are and that you don't lose any negatives. That's the biggest problem I see with kids. They start losing the negatives and the positives. When you grind that in and just give me my answers, negative 6 plus or minus the square root of b squared, well that's 36, minus 4 times a times c all over 2a. Hopefully this is pretty easy. And that would be 6 plus or minus the square root of, well, 36 minus 52. negative 16 all over 2. This becomes 6 plus or minus the square root of negative 16 is 4i divided by 2. Now, we know that this is our answer down here. How can that answer show up over here? Well, there's one more step, and that says everybody here is divided by 2, not just the 6. 6 divided by 2 is 3, and 4i divided by 2 is 2i. So the big thing here is something called the discriminant, and that's b squared minus 4ac from the quadratic formula. Sometimes you just want to find out whether a quadratic has 1, 2, or no roots. This discriminant will tell us. For example, this over here, when we did the discriminant for the other example was negative 16. And when it is a negative as a discriminant, it will never touch the x-axis. And that tells us we have complex or imaginary roots. Now you're saying, aren't complex and imaginary the same thing? Not really, but yeah. A complex is when there is a real part. For example, we had 3 plus or minus 2i. This is complex because it's part real, part imaginary. Or you can have like our first example where it was purely imaginary, where our first example was plus or minus 3i. Then you can say, well, you could say the real part was 0, which makes it complex. So that's why I say it's, yeah, really the same thing. So when is the x-axis only going to be touched once by a parabola? That will happen when the discriminant is 0. When the discriminant is greater than 0, we're going to have real roots. So that's going back to the first page. Back here, I could have done the discriminant for this and found out that its discriminant would have been 0. So for example, this comes from the equation x squared plus 6x plus 9, right? If I FOIL that out, well, the discriminant would have been b squared minus 4 times a times c. This is my a value, this is my b value, this is my c value. And look, 36 minus 36 is 0. So right here is an example of it touching the x-axis once. See, the discriminant was 0. If I come back to this one, if I had written this out, right, that's the equation when I multiply those two binomials out. And if I had done the discriminant for that, b squared minus 4 times a times c minus 28, which is 36. When the discriminant is greater than 0, there are actually 2 real roots. And there were here, 1 and 7. Okay, it would look like that. And then we saw here that if we were to do the discriminant here, remember this is x squared plus, since there is no b value, it's 0. And if we were to do the discriminant there, b squared minus 4 times a times c gets me negative 36. And when we draw the picture of it, voila, there it is. So this page right here is pretty important, so make sure that you get this down. so that we understand that the discriminant can help us discriminate. Discriminate is not always a bad word. You can have discriminating tastes, such as a wine sommelier, somebody who can taste wine and tell you the differences right down to the region where the grape was grown. So the discriminant discriminates the parabola and tells us about it. It tells us if it touches the x-axis once, twice, or never. All right, so example 2, let's solve the following quadratics for their zeros. Now, I may be doing some razzle-dazzle here for you, but this is how fast I expect you to move through a completing the square. So I'm going to do a complete the square, CTS. First thing, I'm going to set this equal to 0. Bring that 7x over, so that's minus 12x. Bring that 10 over, so that is plus 40. All right, this is how fast you do it. So if I bring this over, it's x squared minus 12x equals negative 40. Okay, half of 12 is 6, so this is going to be x minus 6 squared equals, now I think about, I'm adding on positive 36 to that to balance the side, and so that is negative 4. So now x equals, that negative 6 comes over to the other side as positive 6 plus or minus the square root of negative 4. So this is x equals 6 plus or minus 2i. Did I go too fast? Here, let me do another one. X squared. All right, so this 10x comes over here to make that 6x. But you know what? I'm going to bring that 15 over there because that's where it's going to have to end up anyway to get me negative 11. Half of 6 is 3, so this is going to be x plus 3 squared equals, I'm going to add on positive 9, which gets me negative 2. To solve for x, I know I'm going to have to take the square roots. That's plus or minus of negative 2. That positive 3 moves over to negative 3, so I have x. So writing it, these are the roots, negative 3 plus or minus I radical 2, because I have to pull the I out of the radical. Yeah, that was fast. But that's how fast we expect you to be able to do completing the square now. So in your homework that we get today in class, that's how fast I expect you to move.